Welcome to chapter 5.1. Now, chapter 5 is my absolute favorite chapter of the text, all right? And we start off talking about using fundamental trig identities. This is what this section is all about. Now, we will use the following fundamental trig identities to help us evaluate trigonometric functions, simplify trigonometric expressions, develop additional trigonometric identities, and solve trigonometric equations. The reason why I love chapter 5 so much is that it's all about problem solving, all right? It's like putting pieces of a puzzle together. Hopefully, you like puzzles. If you do, you're going to like this section. So let's talk about our fundamental identities, all right? There's a bunch of them that you're going to want to make sure that you are familiar with and know by heart. So, recall our definitions of the 6 trigonometric functions that we studied in chapter 4 when using the unit circle. To evaluate the sine of an angle theta, we found the corresponding y-coordinate. To evaluate the cosine of an angle theta, we found the corresponding x-coordinate. To evaluate the tangent of theta, we took the ratio of the y divided by the x. Our reciprocal trig function of sine, that was cosecant, that was 1 over y. The secant of theta was the reciprocal of cosine, 1 over x. And the cotangent of theta was equal to x divided by y. All right, so this is information that you guys already know, our unit circle definitions. Now let's talk about how we can apply them to come up with some of our identities. And the first ones we're going to talk about here are our reciprocal identities. So let's look at this definition for the cosecant of theta. The cosecant of theta is 1 divided by y. Well, if y is equal to the sine of theta, that means I can substitute sine theta in for y into this expression, giving me the cosecant of u is equal to 1 over the sine of u. Again, all we did is we replaced y with sine. Now, you might be asking, why are we using the letter u? Well, throughout your mathematics careers, you're going to begin to study some more u substitutions. Basically, u is just representative of any variable. If you don't like the u's here, you could throw in an x, you could throw in a theta, you could throw in a y, right? Whatever works best for you, all right? But we're going to use the letter u in this case, again, just representing any variable. So the cosecant of u is equal to 1 over the sine of u. And if we solve this equation for sine, notice we can multiply both sides by sine u and then divide by cosecant u, we get the sine of u is equal to 1 divided by the cosecant of u. We could do the same thing with the secant of theta. Secant of theta is equal to 1 divided by x. Well, if x is equal to cosine theta, then secant theta must be equal to 1 over cosine theta. Secant u is equal to 1 divided by cosine u. And if we solve for cosine u in this equation, we get cosine u is equal to 1 divided by secant u. All right, our final reciprocal identity applies for tangent and cotangent. The cotangent of u is equal to 1 over the tangent of u, and the tangent of u is equal to 1 divided by the cotangent of u. And we've talked about the reciprocals of trig functions already, okay? So this shouldn't be new to you guys. Notice that the sine of u is equal to 1 over its reciprocal. The cosecant of u is equal to 1 over its reciprocal, right? And the same goes for cosine and secant, tangent and cotangent. Those are our reciprocal identities. Next, we have the quotient identities. All right, let's look at this definition for evaluating tangent of theta. Tangent of theta is y divided by x. Well, if y is equal to sine theta and x is equal to cosine theta, then tangent of theta must be sine theta over cosine theta. Or tangent of u is equal to sine u divided by cosine of u. We could also flip that and look at the reciprocal. That means cotangent u is equal to cosine u divided by sine u. Notice again, cotangent is defined as being x over y. X is cosine, y is sine. Cotangent theta is cosine theta divided by sine theta. All right, reciprocal identities, quotient identities. Let's move on to the next set of identities. Also recall that the unit circle is a circle of radius 1 with a center located at the origin. It is defined by the equation x squared plus y squared is equal to 1. You might recall from way back in chapter 1 when we talked about circles, we had the standard form x minus h squared plus y minus k squared is equal to r squared, where h and k were the center. Notice h and k are going to be 0, 0. Our center is right here at the origin. Okay, and r, well, it's the unit circle, so the radius is 1 unit. 1 squared gives us 1. Well, as we said before, our definition using the unit circle and evaluating the cosine of theta was equal to x. We also said that the sine of theta was equal to y. So what we can do is we can take this equation for our circle, and instead of x, I can replace x with cosine theta, and instead of y, I can replace y with sine theta. That gives me the cosine of theta squared. The sine plus the sine of theta, quantity squared, is equal to 1. And that brings us to our first Pythagorean identity. Cosine squared theta plus sine squared theta is equal to 1. All right, one thing to make note of here, okay? Cosine of theta, quantity squared. The way that we write that is we put the exponent right after the cosine. Okay, so these mean the same thing. The reason being, we don't want to get confused with something like this, cosine of theta squared. This means the cosine of the angle squared. All right, so if you see it written like this, that's cosine of the angle squared. That's not what we want in this case. We want the entire value, cosine theta squared. Therefore, we represent that by putting our exponent right after the cosine. Same thing with sine. The sine of theta, quantity squared, that is written as sine squared theta. All right, so cosine squared theta plus sine squared theta is equal to 1. You'll see this listed as the Pythagorean identity. Sine squared u plus cosine squared u is equal to 1. Notice we switched the order, but again, a plus b is equal to b plus a. Okay, doesn't matter what order those come in. And we replaced our thetas with u's. Again, you can have any variable in there that you want. Okay, the u's are just representative of some quantity. All right, there are two other Pythagorean identities that you guys need to know. Now, if you remember this first Pythagorean identity, okay, we can derive the other two. We can derive the other two by taking both sides of our equation here and dividing by cosine squared u. All right, and I'm not breaking any rules of algebra here. Okay, right? When I divide the left-hand side of the equation by cosine squared u, I also divide the right-hand side of the equation by cosine squared u, right? We haven't broken any rules of algebra. Now we can do some math. Well, using the distributive property of division, I can divide each quantity on the left-hand side by cosine squared u. Sine squared u divided by cosine squared u. Well, as we said before, sine over cosine, that gives us tangent. Therefore, sine squared u over cosine squared u is going to be tangent squared u. Cosine squared u divided by cosine squared u, well, any value divided by itself is 1. So we've got tangent squared u plus 1 is equal to 1 over cosine squared u. Well, 1 divided by the cosine of u, that was equal to the secant of u. So 1 divided by cosine squared u, that's going to be equal to secant squared u. And that gives us our next Pythagorean identity. Okay, we have got tangent squared u plus 1 is equal to secant squared u. All right, so again, we obtained the second Pythagorean identity by dividing everything by cosine squared u. To get the third Pythagorean identity, we just start with this first one again, and instead of dividing everything by cosine squared u, we divide everything by sine squared u, both the left-hand side and the right-hand side of the equation. Well, if I do that, sine squared u divided by sine squared u, that's going to give me 1. cosine squared u divided by sine squared u. Well, cosine over sine, that's cotangent. So cosine squared u divided by sine squared u gives me cotangent squared u. And 1 over sine squared u, well, 1 over sine theta is cosecant theta. 1 over sine squared u is going to be cosecant squared u. Doing out that algebra, we get our third Pythagorean identity. 1 plus cotangent squared u is equal to cosecant squared u. All right, so there we have our three Pythagorean identities. Okay, if you remember the first one here, sine squared u plus cosine squared u is equal to 1, we can derive the other two. All right, our last set of fundamental identities. Also recall that the shapes of the graphs of each trig function. So we talked a lot about graphing, right? Here we have the graph of y equals the sine of x, y equals the cosine of x, and y equals the tangent of x. Way back in chapter 1, we studied even and odd functions, and we said a function was even if it had symmetry about the y-axis. All right, and if it was symmetric about the y-axis, that meant that evaluating f of negative x gave out the same thing as evaluating f of x. Plugging in negative x gave out the same value as plugging in positive x. F of negative x equals f of x. That was y-axis symmetry. The function was even. A function was said to be odd if it was symmetric with respect to the origin. Origin symmetry is also known as xy symmetry. This meant that if we plugged in negative x for x, we got out the opposite of the original function. All right, evaluating the opposite of x gave us negative 1 times f of x. So, based off of these graphs, let's start with sine here. Our sine function has origin symmetry. If I reflect this graph over the x-axis and then the y-axis, I end up with the exact same image. Therefore, sine is going to be odd. Because of that, if I evaluate the sine of negative u, I can rewrite that as negative 1 times the sine of u. Cosine, on the other hand, is an even function. Notice that we have y-axis symmetry, right? If I reflect that over the y-axis, I end up with the exact same thing. That means plugging in the opposite gives me out the same as the original. All right, the cosine of negative u is equal to the cosine of u. Plugging in negative u will give out the same thing as plugging in positive u. All right, and finally, we've got tangent here. Tangent, this also has origin symmetry, xy symmetry. Tangent is also an odd function. Therefore, the tangent of negative u is equal to negative 1 times the tangent of u. The same can be said for each of their reciprocal functions. The reciprocal trig function of sine is cosecant. Therefore, cosecant is also going to be an odd function. The cosecant of negative u is equal to negative cosecant u. The reciprocal of cosine, well, the reciprocal of cosine, that's going to be secant. We have the secant of negative u is equal to the secant of u. That is an even function. And then we have the reciprocal of tangent. That's cotangent. That's also going to be an odd function. The cotangent of negative u is equal to negative 1 times the cotangent of u. All right, and one more. All right, I might have said that was the last one, but these are actually the last ones. All right, our last set of fundamental identities are the cofunction identities. So, cofunction. What does the word cofunction mean? To identify cofunctions, simply add the prefix co to a trig function if it does not begin with co, or take the prefix co away if the function begins with co. Literally. All right, the cofunction of sine is, well, sine does not have a prefix of co, so we add a prefix of co to sine, and we get cosine. The cofunction of sine is cosine. Similarly, the cofunction of cosine, well, this has a co, so to find the cofunction, I get rid of the co, and what's left over? Sine. The cofunction of cosine is sine. The cofunction of tangent is, I put a co in front of it, cotangent. The cofunction of cotangent is, well, it starts with a co, so I get rid of it. That leaves me with tangent. And the cofunction of secant is, I add a co in front of it, I get cosecant. The cofunction of cosecant, it starts with co, I get rid of the co, is going to be secant. So what is our relationship between our cofunctions? Well, here we have these cofunction identities. The sine of pi over 2 minus u is equal to the cosine of u. The cosine of pi over 2 minus u is equal to the sine of u. The tangent of pi over 2 minus u is equal to the cotangent of u. And the same can be said for each of their reciprocals. So the neat thing about these cofunction identities, okay, is you might look at them and you're like, oh man, I have to memorize all 6 of these. Well, the only time you're going to use these cofunction identities is when you see a pi over 2 minus u, a pi over 2 minus something, inside of one of your trig functions. And whenever you see that, all you have to know is you're going to change it to the cofunction. So what's the cofunction of sine? Cosine. All right, so the sine of pi over 2 minus u just becomes the cosine of u. The cosine of pi over 2 minus u, well, what's the cofunction of cosine? Sine. This becomes sine u. The tangent of pi over 2 minus u, what's the cofunction of tangent? Cotangent. Becomes cotangent u. The cosecant of pi over 2 minus u, well, what's the cofunction of cosecant? Secant. Therefore, this becomes the secant of u. The secant of pi over 2 minus u, what's the cofunction of secant? Cosecant. This becomes cosecant u. Cotangent of pi over 2 minus u, well, what's the cofunction of cotangent? This becomes tangent of u. All right, so those are all of the fundamental trig identities. All right, make sure you have them all written down and in your notes. They are going to come in handy when we are completing all of the next problems. All right, keep them handy. We're going to have some good problem solving coming up.